All right. Hello, everybody, and welcome. I'm working on the micro valve for the micro linear actuator of the robot hand. It's a lot of information, so I have to go quickly. Let's see what we're looking at today. Isn't that nice? This is the roadway that leads you to a human mimicking robot hand. And we're looking at the colonnade of San Miguel. I don't know how to read the rest of this. But there it is. Hopefully we'll get down there. And I have to go fast. I do try to put my videos on my YouTube channel. The name of the channel is Patrick Gray. I invite you to subscribe. I think you'll like it. I have a website. The menu includes give the robot a hand. That's where this is. Anything real could hurt somebody. So manage a real item in a manner that is safe and reasonable and legally allowed. If you can't manage it that way, my advice is don't create it. I understand that most people are going to say the hand that I've created is impossible. I don't think so. I'm going to show you all this. This is the robot hand in key shot. It's at 48. When it gets to 128, it's really pretty. I like key shot, but I can do the details faster in SketchUp. These are the little micro linear actuators, micro hydraulic cylinders that control the motions of the hand, and the micro valve is what allows us to control how these are moving. I'm going to switch to SketchUp. This is a working drawing in SketchUp. We took a cube of 2205 alloy stainless steel and we're going to drill channels in it. The purpose of this, if you drill these two channels, one channel goes through the stem and the other channel brings it to the connection, and so it allows you to have a right angle connection inside this block. And we're doing it this way because we can make this as small as we want, and as you get it smaller, you can't do this with tubing. These cylindrical channels will be created by the electric discharge machining, and once we get them built, we'll plug them with these plugs so they don't leak, and you wind up with a finished product where you have a right angle connection going from here to there or going from here to there. So this goes down into there, and these are plugged. This is the iGlide polymer bushing material, and inside of that is the stem of the valve. And what happens, see, the stem has holes in it. Now, they only need to be 0.6 millimeters in diameter. That's all we need for this work. That's why this is being done with the electric discharge machining, to get something this small. This stem goes inside of this polymer bushing. The polymer bushing has an asymmetrical shape, so that when it's put into this valve body, it won't rotate. And we look at the way the stem moves, and if you take the stem and turn it to there, this hole is not lined up. You'll notice the distance from here to here. That distance is what keeps it from leaking, and that is affected by the diameter of the stem. That's why the stem has that diameter. But these two holes are lined up. So this is one condition of the valve. The middle condition of the valve, so you see we move this down by 45 degrees. Everything is blocked. Notice how close this gets. That's why the valve stem is this diameter. But nothing can move because everything is blocked. And if we continue to turn it even further, you'll notice that these back ones were lined up in this condition, but up here, the front ones are lined up. And so what we can do is change the way the valve is controlling the hydraulic cylinders depending upon how the stem is turned. And the question that comes up is, how hard is it to turn this stem? This stem is basically 4 ball valves stacked together with a common actuator. And I'm going to work through, I hope, what I think is how you calculate what force is needed to turn this stem, because until you know what force is needed, you don't know what the motor is going to be. I think it can be done with one of these open frame spur gear motors, and you want to use these because they cool well, they're very small, they have a lot of torque, and this only for the RPM, and the RPM only needs to be 50 RPM, and that is because the human muscle obtains its maximum force in 150 milliseconds. So this has to go from closed to open in 150 milliseconds. So if it travels 45 degrees and 150 milliseconds, that's 50 RPM. So it doesn't need to turn any faster than that. All right, now I got to go really fast. This is a Corel Draw page that I created. I'm going to convert this to a PDF and put it on my website at that Give the Robot a Hand page so you can download it. This is the little micro cylinder that we have, the piston rod and the piston head. The area of the piston rod is 0.0025 square inches. The metal has a yield strength of 65,000 pounds per square inch. So this rod can take 162 pounds of tension and usually 81 pounds of compression. From the literature, they tested hands to get the abduction, adduction, and flexion extension force that fingers can create from the intrinsic muscles of the hand. It comes out to 40 newtons. 40 newtons is 9 pounds. The force that this needs to create, we can't use this size because the other side of it, you have to subtract the area of the rod. So this is 0.0156 square inches. The area of the rod is 0.0025 square inches. So that difference is 0.0131, and we want 9 pounds from 0.0131 square inches, and that gives us a pressure that we need of 687 pounds per square inch. And that hydraulic cylinder can do that. It can go up to 3,000 pounds per square inch. The stem is pushed into the eye-glide. The eye-glide is a compressible solid, so the stem has a larger diameter than the cylindrical opening in the eye-glide, and when the stem is pushed in there, the eye-glide pushes on it. And if the eye-glide is pushing on it at a pressure greater than your hydraulic pressure, it won't leak. And so we're going to use 900 pounds of pressure, and the surface area of the stem is 0.1345 square inches. And the radius that this rotating force is exerted against is a radius of 0.04 inches. And the coefficient of friction of the J200 eye-glide plastic is 0.1. And this allows these thoughts. First of all, the piston rod can withstand 162 pounds of tensile strain. It can withstand basically half of that, 81 pounds of compressive strength. So it has more than enough strength to create 9 pounds. 40 newtons is 9 pounds. We take the subtraction of the big side piston head square inches minus the square inches of the rod, gives 0.0131 square inches that we're using. 9 pounds of force divided by that surface area gives 687 pounds per square inch. We'll use 900. The surface area of the stem is 0.1345 square inches. 0.1345 square inches times 900 pounds per square inch is 121 pounds of force. However, the coefficient of friction is 0.1. So we have 13.3 pounds of force of the eye-glide squeezing on the stem. this 13.1 pounds of force is applied at a radius of 0.0425 inches. This torque of 13.31 pounds at 0.042 inches equals this number, which is 0.565 inch-pounds of torque. 0.565 inch-pounds of torque is 650 gram centimeters, or 0.65 kilogram centimeters, or 6.5 kilogram per millimeter, or 65 millinewton meters. So that's the torque we have to create in order to be able to turn the stem. And I went to this website to look at these motors because this website has a PDF that talks about their motors, and it gives specifications for their motors. I think there are plenty of companies in China that make these, but at least this has numbers. And it tells you different ways that it can create. Here is one that has a shaft that comes out the end of it. And this is the dimensions of it. 15 millimeters by the length. If you're less than 1,000 to 1, the length is 9. So it's 24 millimeters by 12 millimeters by 10 millimeters. They advise using loads well under the limit of the stalling amperage. So you have to go look at that. And this set of motors at 50 RPM, and here is 6 kilogram millimeters, and here is the current, which is way below their max current. And so there's a motor that we can use, and that's how you do this. Okay, and here is the little motor connected to the valve, and here I measured my forearm. My forearm is 4 inches by 4 inches at the elbow, and 2.75 inches by 1.75 inches at the wrist. And we have 17 of those hydraulic cylinders in the arm, and you can see that they fit in there with space left over in the forearm, because the forearm is going to have these big muscles here to give the strength of the hand. That's a separate calculation. And so we're back in SketchUp. Here is the finger grabbing a rod, and here is a force analysis. Basically, in order to do it, this is pulling with 113 pounds of force. And the next thing to look at is you look at how long are these ligaments when the finger is curled up versus how long, see, it goes to this anchoring point when the finger is straightened out. And you can get the surface area of this and divide it by the circumference of it, and it'll give you the length. And the length is about 1.25 inches or 1.5 inches. So we have to have, I forgot to mention, this distance is about 4.5 inches. This distance from here to there is about 4.8 inches. So it's 4.5 inches wide. The finger is 4.8 inches long, and this thickness of the hand is about 2 inches. And so we got to, for those strength, we have 2 of these strength tendons for each finger and 2 for the thumb. So that's 8. And we're going to put 4 of them on here to move the fore part of the hand, and we're going to put 4 of them down here to move the hand at the level of the wrist. So that's 8, 12, 16. So we got 16 of those tendons in the forearm. And the hydraulic cylinder that gives the big power is in the forearm, and it needs to be maybe 2 inches long. And this is about 1.6 inches. So that's 3.6 inches for each one of these. And we need to get 12 of them in there. And I think we can do it. I just haven't drawn it out, but that's a teaser. I'm teasing you. I'm going to show you, I think. We're going to have a hand out here that has 17 connections to the micro hydraulic cylinders for the intrinsic muscles of the hand, and it has 16 connections to give the strong power of the hand. And so there you have it. And she is again holding her palms up and pointing at me. I think it means I need to stop. So that'll be enough. We'll do some more.